Hello, I'm Richard Kirby. Part one of this presentation is about 30 minutes in length. The objective is to explain some of the background to non-normal distributions. So when you see such a distribution, to make a prediction, and remember a capability index, which uses distributions, is a prediction about the quality being offered. It means that you can then be confident about the way you handle distributions. It means that you are being truthful to your customers in the report that you provide to them. Before I start talking about the process of preparing and interpreting distributions, which will happen in part two of this course, here in part one, I start by reminding you about the role of the qualitician and those topics which are important if we are to understand how to work with distributions, both normal and non-normal distributions, how to put them into context of supplying product to a customer. We are qualiticians. Few people understand our role, but quality as a subject is becoming increasingly key for business, all business, not just manufacturing. Measurement and the predictions we make from those measurements is in turn an important aspect of our work. Increasingly, customer expectations demand that we supply lower and lower quantities of defects in the product we deliver. And the only way to achieve this is through an improved understanding of the process, which in turn is done by better measurement and analysis of the process, which will almost certainly require using distributions. And distributions are only one small topic of the many we use in quality. I often say that there are four major areas of quality. People. People have a greater influence on the process than anything else. So we must manage our people well, especially when it comes to change management, building balanced teams, recognition, and so on. Systems, we must manage the array of ISO standards, audits, procedures, and work instructions. SPC is all about measurement and using statistics for the classic predictions. Can we make it to spec? Are we making it to spec? Have we made it? Could we make it? And my fourth area, problem solving or improvement. They're one and the same, and they are at the heart of quality. 30 years ago, Juran was explaining how companies who ignore continuous improvement would disappear. I have a slide somewhere showing all the package making companies in the UK that have disappeared, almost certainly because they allowed their competition to improve at a greater rate, making better quality at a lower cost. Can you remember Crosby's book, Quality is Free? Get rid of the defects, and in one move, you reduce costs and improve quality. Yep, quality is doing things right when nobody is looking. Let's look at the 6 topics which I associate with the use of distributions. I shall mention these 6 topics, all associated with the management of quality in this presentation. How specifications influence our work. The purpose of inspection. What measurement can and can't do. The 2 myths around critical parameters. Why bother with the complexities of distributions when we can simply count the number of defects, I hear people say. That's a dangerous thought. And how you may unwittingly be cheating when you carry out a capability study, providing a fake statistic. So the first of our associated topics is specifications and the influence which they have on the quality that we deliver to the customer. Let me ask you a question. You don't need to answer me, but you do need to be honest with yourself. When you supply product, which is out of specification, do you tell the customer the proportion of your supply which is out of spec? Your answer is probably, we don't knowingly supply defective product. How important is it for you to supply product which is in specification? On a scale of 1 to 4, or put another way, at which of these 4 levels do you associate your own culture? Do you just keep quiet, as normally customers don't notice, which possibly means that you have a culture where it's okay to supply out of spec product? Or do you just accept that you should have a tighter inspection level next time? Or level 3, do you rely on your quarantine sorting system? Or finally, level 4, because you know the customer will send it back, you arrange to deliver it to a less demanding customer. Yes, I know in part it depends on the criticality of the feature, which you have found to be out of spec. In which case, we have to decide whether the specification is correct or not. Why is there a tolerance if people ignore it? Still on the topic of specifications, another question for you to consider. Here is the distribution of results from our process. Is there a significant difference between product which is just outside specification limit and product which is just inside the specification limit? Think about, how was the specification originally set or reviewed? Who set it? When was it set? Really, there is no difference between these 2 classes of product. It's not a case that it suddenly becomes unacceptable, but more a case of, as we move away from target, the quality deteriorates. Although we would like all the product we produce to be on target, what is the difference between product being produced in this very capable process and product which is just inside specification from this process, which is just capable? We try to manage our process so that we produce precise quality product. But so often we have a variable process like this. Within a delivery, we find a distribution of dimensions, as shown here, in decreasing amounts as the dimension moves from the target. How does this product of a different dimension to the target spec perform at the customer's plant or in the hands of the consumer, compared with product which is on target? At what dimension does it become unacceptable to deliver the product? I've already said that I do not believe that at the spec limit, it suddenly becomes unacceptable. Do you recognize this conversation? A quick check on the product prior to dispatch revealed a prediction for the quality of the delivery that was not good. Quality manager. The product's out of spec. The PPK is 0.5, therefore we must not deliver it. Production manager. It may be out of spec, but look, only just, and it would be difficult to schedule a replacement production run. Purchasing manager. It'll be another 3 days before we can get new raw material. Sales manager. I promised the delivery for tomorrow to meet an urgent order they have. They are too important to let down. Anyway, look, there was only 1 piece in the sample out of spec. Factory manager. I'm sure it will be fit for purpose. They won't notice. And with month end approaching, I don't want that extra scrap on the books. So, if this is allowed to happen, what is the point of a specification? Critical parameters, more questions for you. Must the critical parameters always be in spec? Surely, for a truly critical parameter, all parts must be in spec. Or they're not critical, are they? If you can supply product with significant quantities of critical parameters out of spec, and the customer does not complain, then it seems to me that you can save time and money by not controlling them as closely. So, how is it decided if the parameter is critical? How do we compare criticality between parameters? Is there a unit of measure for criticality? Oh, the height is 4 crits. Thickness, oh, that's only 2 crits. But ovality, that's 8 crits, and so on. Who in your operation decides on specs and criticality? I repeat, specs should be seen as a science, not left to guru's experience, which may be out of date and based on inappropriate influences. A final thought on specs and critical parameters. The criticality of a parameter defines if we need to measure. We only need to measure those parameters which are critical. That is apart from a setup when everything gets measured. The stability of the process defines how often we measure. The frequency of measurement is decided by the process stability, not the fact it is critical. If your process never changes, you can afford to check it infrequently because history or experience says it will not change. So before we start creating distributions of data we collect, perhaps we should review our critical parameters. Are they really critical? Do the number and type of capability or complaint reports suggest a change is needed or is possible? Consider relaxing the tolerance, improving the process, changing the frequency of checks, removing the parameter from the list of criticals. Which brings us to our next associated topic. What does inspection achieve? Delivering even one defective piece is a potential major complaint. For example, if a can from another batch gets mixed in with delivery, the ingredients on the label are incorrect, that could lead to an allergic reaction in a consumer. Or poor lacquer cover that leads to leakage. And then a food critic publicly criticizes the product. Many managers believe that inspection is carried out to stop defective product reaching the customer. No, it's not. The purpose of inspection is to ensure the product is made correctly. The objectives of making it correctly is different to an objective of accepting we make some bad, but trying to ensure that only the good stuff reaches the customer. We want to make it right first time. As we know, once defective product is made, some of it will be delivered. And in any case, we make more profit if we only make good stuff. Here's another question to ask yourself. How effective is your inspection at helping you to make good product? Again, as we've been hearing so often in recent times, we should be guided by science, not historic dogma, nor standards set in the past. Many control plans are no longer valid because the machines in the process have changed or the raw materials are different. Yes, there is a science for both establishing the sample size for control checks and the sample sizes for sorting quarantine stock. Measurement is not about deciding if product is good or bad. It's about controlling the process. Briefly, I must mention automatic inspection. Those systems that use special sensors or cameras. They are really useful, but they do not provide a foolproof sorting system. Yeah, most of the good product is accepted and the defective product is rejected. But automatic inspection machines make mistakes. Good parts get scrapped, defects accepted. These are the alpha and beta errors of the machine. And alpha and beta will never be zero. Advances in technology mean it's getting better with smaller alpha and beta, but it's still an issue. However, these devices are fabulous to monitor trends in your process and really good for providing data on rejects, which we can analyze for improvement projects. For example, the black marks are increasing. What is causing this? To supply a customer with defect-free product, there is only one solution. Make good stuff. Manage the process so none are made. Do this by good setup, reducing variability, and stabilizing the process. Present performance of the defect levels in the packaging industry varies from process to process. The best is measured in parts per billion defective. The worst, probably 5% of all parts produced are out of spec. Here's a table of levels of defect with my view on subjective bands and the associated capability. You can see 5%, 50,000 parts per million, PPK of 0.65, totally unacceptable. Right to the other end, excellent, 100 parts per billion, 0.1 parts per million, PPK of 1.78. This is my perception of the influence of setup, capability, and stability on the resulting ppm defective produced, and also its influence on the capability of the process. With no control over setup, variability, nor stability, you are likely to produce more than 10,000 parts per million, or 1% waste. As you improve the management of your setup, the defects will reduce. Reducing variability of the process leads to further defect reduction, and by achieving a stable process, you can expect even more reductions in defects and reductions in scrap, and you will save money. Again, good quality costs less. This is one of my favorite cartoons. There's nothing that the two managers are doing with their checks that will make the final output acceptable. Almost certainly, they're using inspection here to apportion blame. Inspection will not improve the result. We can all see that there is a problem to be solved and a lot of work and materials have been wasted. The inspection is being done too late. Yet so often, there is a disconnect in managers' brains that makes them think inspection of finished goods means customers get good product. No, it's inspection of the process that does this, not the product. Often we measure the product to understand the process. My next topic is the limitations of measurement, what measurement can do for you and what it cannot do. Let's consider a 10-head machine. We all agree that the machine setup or process setup is important, but it must be done correctly if we are to produce good product. The issue comes in deciding what correct setup is. One of the classic causes of poor setup or incorrect setup is trying to set up a machine by taking just one measurement per head. For this illustration of a correct setup, I've taken 3 measurements from each head and now have a clear picture to decide whether and how each head is to be adjusted. With just 1 measurement per head, we would have a random dot somewhere in the confidence interval of the 3 sample plot. On the whole, this wastes time. This procedure requires us to adjust according to how far the average of the 3 results lies from target. Should the target fall within the confidence intervals, then we do not adjust at all, and so on. In this example, by using this procedure, defects were reduced from 15,000 parts per minute, per million defective, which were being produced, down to just 1,500 parts per million. Had we used a procedure where adjustment was based on a single result, there would have been both over and under adjustment and no improvement at all from that initial point. One use of measurement is to produce the control chart, the X-bar chart, or sometimes known as the Shewhart chart. We expect to see some variability in the process, and the control limits tell us what variability or fluctuation in the process we can reasonably expect to see. This visualization of the process means we shall not react without good reason. When measurements go outside the control limits, we can say with confidence that the process has changed and we must act. And here again, it has changed. And we need to ask, why has it changed? So we can prevent that happening again, save time in the future. Using control charts like this is continuous improvement. Yep, measurement can tell us if the process has changed in setup, but it cannot tell us if the product is good. Another statistic we estimate from measurement is capability. It is the means by which the customer predicts whether the quality of product being bought is fit for purpose. You know it as capability index. This delivery is near perfect at a PPK of 3.6. This one is borderline at best, with 20,000 parts per million outside the tolerance, some above, some below. PPK 0.78. In this process, although precise, half of all the parts are above the spec limit. It will be necessary to quarantine the production and sort it. PPK 0. In this final process, simply improving the setup would have the potential of improving the PPK immediately to 2.3. Again, capability predicts the proportion of the delivery within tolerance, but it cannot tell you which pieces are good and which are defective. Earlier, I asked, how is it decided if the parameter is critical? How do we compare criticality and so on? It's important that you know where your critical parameters are to ensure the process is well managed. But there are some myths about critical parameters, and you need to be aware of these. A critical parameter is established through trials, not historical dogma, defined by a guru who ruled the process in years past. If you ask, how do you decide which parameters are critical? Often people will not know. Critical parameters were possibly decided years ago and never have been changed. If we ask, is there a review? Almost certainly the response is No. Why do we need to? Carrying out FMEA, failure mode effects analysis, is a first step to establishing if the parameter is likely to present a high risk of producing bad product. The modern approach to determining which parameters are critical is to have a program of understanding the process, which involves a plan, trial, and provides a picture or Pareto chart of the parameters. If your customer never complains about quality of the critical parameters you have defined at the output of your process, then the chances are that you have the process under good control. Yes, you have good management or have stabilized the process. Managing a critical process is expensive, with all the time to measure and record and adjust. With a stable process, you can potentially save money by reducing the frequency of checks and adjustments. So get them stable. This critical process of the container height is so stable that it is only checked at setup. Why should I spend extra time and endure problems in finding a distribution that fits my data? Why can't I just count how many pieces in the sample are out of spec? Well, using distributions to predict gives the wrong answer 1 in 20 times. And we tend to remember those times when it's wrong. But simple counting gives the wrong answer 15 times out of 20. But we tend to conveniently forget those errors. Counting was used when we inspected every piece that was made, a far cry from the mass production of packaging today. Counting provides a more optimistic but fake view of quality. Yeah, it's easier to count, hence its popularity, but it's dangerous. If we just count how many defective cans we have, we learn nothing. Experience also tells me that if one out-of-spec piece is found in the sample, operators wanting to please the manager and avoid extra work can quickly find one in spec to replace it and hoodwink everyone that things are fine. Yep, counting provides a more optimistic view of quality, but it tends to be wrong unless we have vast sample sizes, typically sample sizes of 10,000 or more. Imagine that you have a pallet of cans to check. You take 5 cans from the pallet. The height of all 5 are in specification. What have you learned about that pallet? Nothing. Our 5 cans again. The spec, 100 plus or minus 5. Those are the 5 can heights. Yeah, all are in spec. Average, 100.1. Standard deviation, 1.57. From this data, we can fit a curve which predicts the heights of all the others on the pallet. Now we have confidence to deliver. On another day, another line, another customer. We take 5 cans. Spec, still 100.5. These are the 5 can heights. Again, all are in spec. Because all are in spec, should we have the same confidence, the same prediction that it's fine to deliver? Let's continue with the distribution method. Average, 100.5. Standard deviation, 11.80. From this, we can fit a curve predicting the heights again. And now we can see there is a problem. So yeah, it's quicker and easier and prone to cheating if we just count, but it gives us false view. The use of a distribution gives an estimate of the number of pieces out of spec. To get an estimate of similar confidence by counting, you will need to check thousands more samples. By counting just a few, we have no understanding of variability within production, just whether the sample is in or out of spec. The power of using distributions. Do you cheat when making a capability study? Well, I say cheat unintentionally, of course. Capability studies and distributions are almost inextricably linked. The capability study is only valid if the curve fits the data. There are lots of curves to choose from, but if none fit, you need to rethink your approach for the study. Here is the data I have collected and allocated into bins. The computer will use the average of the data and the standard deviation of the data, as we've just seen, to create a normal curve. You can no longer say, in defense of a bad decision, well, that's what the computer told me, because I'm telling you that you need confidence that the curve matches the data. And in this example, it doesn't. Sometimes there is a non-normal distribution we can use to fit the data, but often your data is just plain unpredictable because it comes from an unstable process. This is what part 2 of the course will be about. If it's a poor fit, then you're cheating. So, summary of distributions in the context of managing data. If you are supplying any product which is regularly out of tolerance, what's the point of the specification? Even 100% inspection will not make defective product good. We measure to manage the process, to keep it making good product, not to sort the good from the bad. Critical parameters change. Customers change their process, so different dimensions become critical. Raw materials change and can change the characteristic of your process. Machines change, and so on. So review your critical parameters. Counting became ineffective years ago. But counting with automatic inspection machines is useful today because of the large sample sizes. Distributions must fit the data or are of little use in making predictions. In today's world, industry expects our decisions to be made on science, not on dogma, nor the experience of times or processes from the past. Guessing about processes is useless because we all have bias based on our experience and what we happen to have seen. Science only manages to get it right 95% of the time, which is a great deal better than guessing 5% correct. And finally, if you believe management of data is an art, don't let your customers know. Coming in part 2, which will complete the course, it will include these topics: the process to prepare any distribution of data, fitting normal or non-normal data to a curve, step from distribution to PPK, challenges that we face when things do not go smoothly, what to do when the data will not fit, and here's some contact details if you'd like to contact me. Thank you for listening to this, and very shortly, part 2 will be available.